Today's topic is Joule-Kelvin effect or Joule-Thomson effect. Joule and Kelvin proved by porous plug experiment that if a gas expands adiabatically from a region of constant high pressure to a region of constant low pressure through a porous plug, its temperature changes. This effect is known as Joule-Kelvin effect or Joule-Thomson effect. So, if we expand the gas adiabatically through a porous plug from a region of high pressure to low pressure, then its temperature changes. Its temperature may be increases or decreases. It depends on its initial temperature. Now we will see what is the porous plug experiment performed by Joule and Kelvin. And we will prove that enthalpy remains constant in this process. This porous plug experiment is shown in this diagram. These dotted lines shows porous plug through which the gas can pass. On two sides of this porous plug, we have two chambers. On left hand side, chamber 1, and in right hand side, chamber 2. Also, we have movable pistons on chamber 1 and chamber 2. These pistons are thermally insulated and the entire chamber is also thermally insulated because we have to expand the gas adiabatically. In adiabatic process, there will be no exchange of heat. So, these pistons and the entire apparatus is thermally insulated. Let a gas is allowed to expand adiabatically through a porous plug from a region of constant high pressure to a region of constant low pressure. Chamber 1 is region of constant high pressure and that pressure we write as P1. Chamber 2 is a region of constant low pressure and we write this pressure as P2. Initially, volume of gas is V1 in chamber 1 and when it reaches to chamber 2, its volume increases and becomes V2. Let U1 be the internal energy in chamber 1 and when this gas reaches to chamber 2, its internal energy is U2. So, P1, V1 and U1 are pressure, volume and internal energies of gas in chamber 1 and P2, V2 and U2 are pressure, volume and internal energy of gas in chamber 2. Initially, the entire gas is in chamber 1 and chamber 2 is empty. Then this gas is allowed to expand through this porous plug into chamber 2. Let volume of gas in chamber 1 is V1 and its internal energy is U1. Constant pressure at chamber 1 is P1 and constant pressure at chamber 2 is P2. At the end of the process, entire gas comes into chamber 2. Initially, gas is in chamber 1, and when this is allowed to pass through porous plug, finally this entire gas comes into chamber 2. In chamber 2, now volume of gas is V2 and V2 is greater than V1 because we say that we are expanding the gas. Gas is expanding, it means its volume is increases. V2 is greater than V1 and let its internal energy is U2 in chamber 2. In this process, work done on the gas by left piston will be equal to P1 V1. P1 is constant. Constant pressure P1 is applied to gas at chamber 1 and its volume becomes 0 from V1. Initial volume is V1 and when the gas reaches to chamber 2, its volume becomes 0 in chamber 1. So, the work done by the piston on gas in chamber 1 will be equal to P1 V1. From the formula dW equal to PdV or W equal to integral PdV. P is constant which is P1 and integral dV is V1. So, P1 V1 is the work done by the piston on the gas. In chamber 1, work is done by the piston on the gas. So, work done by the gas is equal to minus P1 V1. In chamber 2, the gas works on piston and the work done by the gas in chamber 2 on the piston, it is P2 V2. So, work done by the gas on right piston is P2 V2 and work done on the gas by left piston is P1 V1. So, net work done by the gas dW is equal to P2 V2 minus P1 V1. Net work done by the gas P2 V2 minus P1 V1. P2 V2 is work done by the gas and P1 V1 was the work done on the gas. So, we write it as minus P1 V1. So, net work done by the gas, we write dW equal to P2 V2 minus P1 V1, equation 1. As the process is adiabatic, there is no exchange of heat because all the surrounding walls and piston all are insulated, thermally insulated. No heat can enter into it or out of it. So, dq is 0 and from first law of thermodynamics, dq is equal to du plus dw and dq is 0. So, we have du plus dw is 0 or du equal to minus dw. Du is change in internal energy. It is U2 minus U1. Final internal energy minus initial internal energy. So, du change in U is U2 minus U1 equal to minus dW. Put the value of dW, which is P2V2 minus P1V1 from equation 1. Now write the terms having 1 in left hand side and the terms having 2 in right hand side. We have this relation U1 plus P1V1 equal to U2 plus P2V2. U1 plus P1V1 is enthalpy H in chamber 1, so it is H1, and in right hand side we have U2 plus P2V2, it is also enthalpy in chamber 2, so we have H1 equal to H2, enthalpy in region 1 equal to enthalpy in region 2, enthalpy H is U plus PV. So it is clear that in porous plug experiment, in Joule Kelvin process, enthalpy remains constant. Now we find the expression for Joule Kelvin coefficient. We want to find what will be the change in temperature delta T. We are changing the pressure. Gas is allowed to pass through porous plug from a region of constant high pressure to a region of constant low pressure. So we are changing the pressure and we want to know what is the change in temperature. So we want delta T upon delta P, change in temperature divided by change in pressure. Delta T upon delta P, it is known as Joule Kelvin coefficient. So we will now find the expression for Joule Kelvin coefficient, as we have proved that enthalpy remains constant in this Joule Kelvin process. So enthalpy H is constant, so its differentiation dH will be equal to 0. And H is U plus PV, so we have differentiation of U plus PV equal to 0. Now it becomes du plus pdv plus vdp equal to 0. Differentiation of u is du and differentiation of pv is pdv plus vdp. First function differentiation of second plus second function differentiation of first. So now we have this relation du plus pdv plus vdp equal to 0. From first law of thermodynamics, we have dq equal to du plus dw and dw is equal to pdv. So we have dq equal to du plus pdv. And from second law of thermodynamics, we have dq equal to tds. If we write dq equal to tds in this first law of thermodynamics, we get tds equal to du plus pdv and du then becomes equal to tds minus pdv. So we find the value of du, which is tds minus pdv, using the first law of thermodynamics and second law of thermodynamics. And now put this value of du from equation 6 into this equation, which is equation 3, du plus pdv plus vdp equal to 0. Here we put the value of du, which is tds minus pdv. Then this equation 3 becomes tds minus pdv plus vdp equal to 0. Two terms are cancelled out, minus pdv and plus pdv, and now this equation becomes tds plus vdp equal to 0. Now we want to find delta T with respect to delta P. we want to find change in temperature delta T, and we are changing the pressure, so we have this change in pressure as delta P. So we want to relation between delta T and delta P, and in this equation we have dP, change in pressure, but in first term we have ds. So we want to eliminate this term of ds. To eliminate this term ds, we write entropy S as a function of T and P, because we want relation between delta T and delta P. So we write this entropy as a function of T and P. If S is function of T and P, then its differentiation ds, we can write it as delta S upon delta T dt plus delta S upon delta P dP. S is a function of T and P. First we take partial differentiation with respect to T, and then we take partial differentiation with respect to P. So ds is delta S upon delta T dt plus delta S upon delta P dP. In first partial differentiation, it is with respect to T, and second partial differentiation is with respect to P. So when we take partial differentiation with respect to T, then we keep P constant, and when we write partial differentiation with respect to P, then we write T as constant. Substituting this value in equation 7, put this value of ds in equation 7. Equation 7 is this: T ds plus V dP equal to 0. Put here this value of ds. So it is not ds. We write from here, put the value of ds in this equation. So we start from T, and inside the bracket it is the value of ds, and then we have plus V dP equal to 0. First term, solve the first term. And take dP common. dP is in these two terms. First term is T delta S upon delta PT with dP, and second term is V dP. So we write this equation as T delta S upon delta T dt plus T delta S upon delta Pt plus V into dP. dP is taken common from the two terms. Now we write delta T upon delta P. First term is of dt, second term is of dP. Take one term to right hand side and find dt upon dP. So dt upon dP from this equation becomes minus T delta S upon delta P T plus V divided by T delta S upon delta Tp. This dt upon dP we write as delta T upon delta P, and write capital H. This capital H means it is enthalpy. It means this delta T upon delta P is at constant H, at constant enthalpy. Now we will use Maxwell's thermodynamic relation for delta S upon delta P T. We will use this relation. Delta S upon delta P T will be equal to minus delta V upon delta T P. Maxwell's relations are relations between these four variables P, V, T and S, If we write alphabetically, then it is PSTV. Look at this relation, and the order PS is in left hand side from downside to upside, PS, and in right hand side we have TV from downside to upside, and a minus sign. Left hand side is partial differentiation with respect to P, and right hand side is partial differentiation with respect to T. So in left hand side, which is partial differentiation of with respect to P, we write T as constant, and in right hand side, which is partial differentiation with respect to T, we write P as constant. So put the value of delta S upon delta PT. We want to eliminate S. So put the value of delta S upon delta PT from this Maxwell's thermodynamic relation, and then delta T upon delta P at constant H becomes equal to minus, delete this T, outside the bracket it is only minus, so correct it, minus, then bracket, minus T delta V upon delta TP plus V divided by, in denominator we write T delta S equal to delta Q from second law of thermodynamics, dQ equal to T ds. So T delta S is written as delta Q. And now delta Q upon delta T at constant P, it is Cp, molar specific heat at constant pressure. From the definition, dQ equal to mc dt, where C is specific heat. Then specific heat C is dQ upon m dt. If we take m mass in moles and we take 1 mole substance, then C equal to dQ upon dt. So we write Cp equal to delta Q upon delta T at constant P. It is molar specific heat at constant pressure P. So in denominator, which is delta Q upon delta T at constant P, it is Cp. So delta T upon delta P at constant H now becomes equal to 1 upon Cp into T delta V upon delta T at constant P minus V. This delta T upon delta P at constant H, we write it as mu, and it is known as Joule Kelvin coefficient or Joule Thomson coefficient. So Joule Kelvin coefficient or Joule Thomson coefficient, it is the ratio of delta T and delta P. We want to find the change in temperature, and we are changing the pressure. So this is the ratio of delta T and delta P, and it is equal to 1 upon Cp into T delta V upon delta T at constant P minus V. This is the expression for Joule Kelvin coefficient or Joule Thomson coefficient. Mu is known as Joule Kelvin coefficient, and it represents the change in temperature for unit change in pressure for 1 mole gas. Now we will find this Joule Kelvin coefficient for ideal gas. For 1 mole ideal gas, equation of state is PV equal to RT. So for 1 mole ideal gas, equation of state is this, PV equal to RT. And using this equation, we can find this value of delta T upon delta P at constant H, which is mu, Joule Kelvin coefficient. Because in this relation we have delta V upon delta T at constant P. This delta V upon delta T at constant P is found by using this relation PV equal to RT. PV equal to RT, so we have RT upon P, and we want to find this differentiation of V with respect to T. We want delta V upon delta T and keep P as constant. So if P is constant, then delta V upon delta T will become R upon P. And put this value of delta V upon delta T at constant P, it is R upon P. If we put this value, then Joule Kelvin coefficient mu becomes delta T upon delta P equal to 1 upon Cp into T into R upon P minus V. Now, from this relation PV equal to RT, in first term inside the bracket in numerator it is RT. So we write it as equal to PV. P is cancelled out, it remains only one, V. So inside the bracket we have V minus V and it becomes 0. So delta T is 0 because delta T upon delta P equal to 0. So delta T is 0. There is no change in the temperature. So in Joule Kelvin process, there is no change in temperature for ideal gas. But if we take real gas, then we will find the change in temperature. Joule Kelvin coefficient for real gas. For 1 mole real gas, equation of state is this. For real gas, equation of state is given by van der Waals equation. This is van der Waals equation of state for real gases. For ideal gas, we have PV equal to RT. For real gases, P is changed by P plus A upon V square and V is changed by V minus B. So, equation of state for ideal gas now becomes P plus A upon V square into V minus B equal to RT. Differentiating this equation with respect to T at constant P, we want delta V upon delta T at constant P. V is in the two terms of left hand side, so we take differentiation with respect to T at constant P. There are two terms in left hand side, so this differentiation is performed by using the formula first function differentiation of second plus second function differentiation of first. First function is P plus A upon V square, second function is V minus B. So we have first function P plus A upon V square and differentiation of second is delta V upon delta T at constant P. It is differentiation of V. B is constant. Then we have second function which is V minus B and differentiation of first. In first we have P constant, its differentiation is 0 and differentiation of A upon V square is minus 2A upon V cube delta V upon delta T at constant P. And in right hand side we have RT, R is constant, so this differentiation becomes R. Take delta V upon delta T common. Delta V upon delta T at constant P, it is in both the terms, take it common. Inside the bracket we have P plus A upon V square minus 2A upon V cube into V minus B into delta V upon delta T at constant P equal to R. From this we find the value of delta V upon delta T at constant P. Also we change the first term. First term is P plus A upon V square. In left hand side inside the bracket, first term is P plus A upon V square. And from this relation, we write the value of P plus A upon V square as it is equal to RT upon V minus B. Put this value of P plus A upon V square here. It becomes RT upon V minus B minus 2A upon V cube into V minus B into delta V upon delta T at constant P equal to R. From this relation we find the value of delta V upon delta T at constant P. It is equal to R upon RT upon V minus B minus 2A upon V cube into V minus B. Substituting this value in equation 9, we get the expression for Joule Kelvin coefficient mu equal to delta T upon delta P at constant H. Delta T upon delta P at constant H is this 1 upon Cp T delta V upon delta T at constant P minus V, and here put the value of delta V upon delta T at constant P. Then we get this relation. This mu is equal to 1 upon Cp T R upon RT upon V minus B minus 2A upon V cube into V minus B minus V. It is equal to 1 upon Cp. In first term, inside the bracket, in denominator, we take LCM, which is V cube into V minus B, or multiply by V cube into V minus B in numerator and denominator. Then we have TR into V cube into V minus B divided by RT V cube minus 2A into V minus B square. In denominator, LCM is V cube into V minus B. Multiply by this V cube into V minus B in numerator and denominator, and we get this relation. Now we divide the first term by RT V cube in numerator and denominator, divide by RT V cube. So in numerator it becomes V minus B. In denominator it becomes 1 minus 2A V minus B square divided by RT V cube. Dividing by RT V cube in numerator and denominator in the first term inside the bracket. Now this becomes 1 upon Cp V minus B upon. Now since B is very small quantity in comparison of V, so in the term V minus B whole square, we write it as V square. Neglect the quantity B. So this term V minus B whole square becomes V square. In denominator we have V cube. So only V remains in denominator, and we have 1 upon Cp into V minus B upon 1 minus 2A upon RTV minus V. Now 1 minus 2A upon RTV, we bring this in numerator and it becomes 1 minus 2A upon RTV to the power minus 1, and we now expand it by using the formula 1 minus x to the power n, binomial theorem. 1 minus x to the power n is minus 1, and the formula is 1 minus nx and the other terms. 1 minus nx becomes 1 plus 2A upon RTV. 1 minus, then minus 1, it becomes plus 2A upon RTV, and other terms we neglect them because 2A is much less than RTV. Other terms are square, cube and higher order terms which are neglected. Now this becomes V minus B 1 upon Cp into V minus B into 1 minus 2A upon RTV minus V. Solve the first bracket. It becomes V minus B plus 2A upon RT minus 2A minus 2A upon RTV. 2AB. It is minus 2AB upon RTB, and 2AB upon RTB, we neglect this term because A is a small quantity, B is a small quantity. So in this term we have, it is not minus 2A upon RTB, it is minus 2AB upon RTB. Minus B is multiplied by 2A upon RTB, it will give minus 2AB upon RTB, and A and B both are small quantities, so this term we neglect it. V is cancelled out as we have V and minus V, and remaining term is 1 upon Cp into 2A upon RT minus B. So this is the expression for Joule Kelvin coefficient for real gas using van der Waals equation of state. This equation represents Joule Kelvin effect for real gases. It is clear that now three cases are arises. Inside the bracket we have 2A upon RT minus B. Three cases are when 2A upon RT is greater than B, this quantity is positive. Second case is 2A upon RT less than B, this quantity is negative. And third case is 2A upon RT equal to B, this quantity is 0. So for first case, if 2A upon RT is greater than B, the quantity inside the bracket is positive, delta T upon delta P is positive, and in the experiment we are decreasing the pressure. The gas is allowed to pass through porous plug from a region of high pressure to a region of low pressure. So pressure is decreasing, delta P is negative. So if 2A upon RT is greater than B, right hand side is positive, then if delta P is negative, then delta T will also be negative and the temperature of the gas will be decreases. So if 2A upon RT is greater than B, delta T will be negative as delta P is negative, and in this experiment temperature of the gas will decreases. 2A upon RT greater than B means T less than 2A upon RB. So when initial temperature of the gas T is less than 2A upon RB, delta T upon delta P will be positive. So value of temperature decreases with decrease in pressure and the gas becomes cool after passing through porous plug. Second case is its opposite. When 2A upon RT is less than B or T is greater than 2A upon RB, then delta T upon delta P will be negative. So value of temperature increases with decrease in pressure and the gas becomes hot after passing through porous plug. Third case is when 2A upon RT equal to B, so that the quantity inside the bracket becomes 0. In this case T is 2A upon RB, then delta T upon delta P is 0, delta T is 0, there is no change in the temperature. This temperature T equal to 2A upon RB, it is known as temperature of inversion. T equal to 2A upon RB is the temperature at which Joule Kelvin effect is 0. It is known as inversion temperature. So inversion temperature is Ti equal to 2A upon RB. It is clear that if initial temperature of gas is less than the inversion temperature, that is 2A upon RB, it becomes cool by Joule Kelvin effect, and if initial temperature of gas is greater than the inversion temperature 2A upon RB, then the temperature of gas will be increases by Joule Kelvin effect. So the gas can be cooled by Joule Kelvin effect if initial temperature is less than the inversion temperature.